in this video, I'll be covering machine learning fundamentals that every AI engineer needs to know. While you'll find endless textbooks and articles on this subject, my goal with this video is to give builders a short and accessible guide to the most critical concepts in machine learning. Here I'm going to focus on 5 key points. I'll first talk about intelligence and world models, then I'll talk about 3 different ways computers can learn world models through machine learning, deep learning, and reinforcement learning. Finally, I'll talk about the most important ingredient in machine learning, which is data. So let's talk about intelligence. Intelligence requires understanding how the world works. But of course, the world is a big and complicated place, so in order to understand it, you need to develop models of the world so that you can compress the complicated and vast reality that we live in into something you can fit into your head. And put simply, a model is something that allows you to make predictions. For example, if you were to look out the window and were to see dark clouds like this, your mental model of the world and understanding that dark clouds typically mean it's going to rain later will allow you to make a prediction that it's going to rain later. We all have mental models of the world that allow us to make predictions and to achieve desired outcomes. And there are 2 main ways that we develop these models. The first is learning from others, like our parents or mentors, and the second is learning directly from our experiences. And as it turns out, computers can learn models of the world in very much the same way. Here I'll talk about 3 different ways computers can develop these models of the world. So here when I say the word learning, what I mean by that is getting computers to do things without explicit instructions. So this is in contrast to traditional software development where programmers use their own intelligence to develop step-by-step instructions for performing tasks or making decisions, and then translating those instructions into computer code. Here I'm going to focus on 3 different ways we can get computers to do things without explicit instructions. The first is machine learning, which is actually an umbrella term for everything that I'm going to talk about in this video. The second is deep learning, which is a special type of machine learning. And then finally, I'll talk about reinforcement learning, which is also a special type of machine learning, but often you'll see it combined with deep learning in modern applications. Starting with way number 1, machine learning allows computers to learn tasks directly from data. And so machine learning consists of 2 key phases. The first phase is called training, and this involves gathering a training data set, so basically a set of examples, passing this training data to a so-called learning algorithm, and the result of this learning algorithm is a machine learning model. Once we have this machine learning model, we can use it to make predictions. So this brings us to phase 2, which is called inference, where we give our machine learning model new data to make predictions which we can use in making decisions or solving problems. Let's dive into a bit more detail on how each of these 2 phases works. So I'll actually start with inference, which is phase 2 because it's a little easier to understand. Inference involves using a model to make predictions. For example, suppose we have this simple linear model for predicting tomorrow's high temperature. The way this works is we take today's temperature high, which is represented by X, we plug it into this equation to make a prediction about tomorrow's high temperature, and this mapping between today's temperature and tomorrow's temperature is determined by these 2 so-called parameters, M and B. The quality of our predictions are going to be determined on how well our parameters are aligned with reality. But you might be wondering, how do we pick these parameters so that these are going to be accurate predictions? That brings us to the training phase, which is where we fit a model's predictions to reality. The key intuition here is that in training, we want to minimize the discrepancy between our model's predictions and real-world data. So the first step in doing this is quantifying the discrepancy between our model's predictions and reality. One way we can do this is through this equation shown here. There's a lot of math on this slide, but I'm going to go through it one step at a time. The first thing to look at is this first term here, which corresponds to the actual values of the quantity we're trying to predict. For example, if we're trying to predict tomorrow's temperature high, y is just going to be a collection of temperature recordings that we collect from reality. The second thing to look at is this term on the right, which are our predicted values. So this is exactly the same equation we saw on the previous slide, but now we've written it out in terms of multiple examples. Instead of just one input x, we have n inputs, x1, x2, all the way to xn. So here are our input values, and then we have our two parameter values, m and b. M gets multiplied by each value in this matrix, and then we just write out this matrix of 1, so we can multiply b by each of these elements to make the math work out here. But you can just think of this as n different linear equations. So m times x1 plus b, m times x2 plus b, and so on and so forth. By taking the difference between these actual values and our model's predictions of the values, we are quantifying the discrepancy between our model's predictions and reality. We call this quantity our loss function. Now that we've quantified this discrepancy, the goal of training is to find the parameter values, m and b, that corresponds to the smallest possible loss function. Well, we could just randomly guess a bunch of parameter values to try to find the one with the smallest loss function. It turns out that we can solve this problem in a closed form using math. The way that looks is we're just going to rewrite some terms. So we'll define this matrix X, which will be all our input values and all these ones stacked side by side. Then we'll put our parameter values in their own little column matrix. Finally, we'll just define our column of actual values as this vector Y. With these new terms, we can rewrite our loss function like this. So we have the norm squared of Y minus X theta. Writing this out a different way, it looks like this. So it's y minus x theta transpose times y minus x theta. And then we can expand this term out and it looks like this. So it looks all long and scary, but you don't really have to worry about that. The key thing to know here is that we can find the values of theta that minimize this loss function by computing its gradient, setting it equal to 0, and then solving for our parameter values. The way that looks is as follows. The gradient behaves a lot like a derivative, which you probably learned in high school calculus. So if we're taking the gradient of L with respect to theta, we can see that this term goes away. This term is linear in theta, so this just becomes this. And then this term becomes this term here. This is our gradient of L. Then we can set it equal to 0, which gives us this equation, and then rearranging it, it'll give us this expression here. And then finally, we can just solve for theta, and those values will be our optimal parameter values. And so if we assume that this matrix here is invertible, then this becomes our optimal parameter values for theta. Okay, so what just happened? We just went through all this math, we computed this gradient, did all this complicated stuff. But here's the punchline. We can get the optimal parameter values for our linear model simply from training examples. So what is X? X is a set of input data that we collect. Y is a set of target data that we collect, and we can combine them to find our optimal parameter values. So put another way, the key point of machine learning is that computers can fit models to reality using data and math. While a linear model is one of the simplest models you can work with in machine learning, this idea of fitting model parameters to real-world data is a common thread you'll see throughout all machine learning models. And just to list a few other popular machine learning techniques you might come across, there's also logistic regression, which is a lot like linear regression, but instead of predicting a continuous target, it predicts a binary target. So that's why it lets you do classification instead of regression. There's also decision tree, which is a fundamentally different way of training models, but it's also very powerful and relatively easy to interpret. And then you have extensions of decision trees by like combining many trees together into a so-called forest, or boosting decision trees on top of each other, like an XGBoost, as well as more traditional approaches like support vector machines, which can be used for both regression and classification. So all the approaches that we see here is what we might call traditional machine learning. While you can go very far with them, they do have their limitations. One such limitation is that often to get these approaches to work well, it requires a significant amount of time and domain expertise to choose the right input variables for your model. For example, we used today's temperature to predict tomorrow's temperature, and so that's probably a pretty good predictor of tomorrow's daily high. However, if we used the number of cappuccinos I drank as our predictor, it might have some sort of correlation with tomorrow's temperature high, but it probably wouldn't do a very good job at this prediction task. So this process of picking the right input variables to your machine learning model is called feature engineering, and it is something that can make or break your model's performance.